Welcome to Tech Disruptions, deep dives into the technologies reshaping industries, from AI to quantum to biotech. Let's get into it.
A new AI chip from researchers at Penn claims to perform operations at an astonishing 4 femtojoules. To put that in perspective, that's orders of magnitude more efficient than even the most cutting-edge AI accelerators today. It sounds like something out of science fiction.
It certainly does. The headline number, 4 femtojoules per operation, is genuinely eye-popping. For context, typical state-of-the-art digital AI hardware operates in the range of hundreds of picojoules per operation. A picojoule is 1,000 femtojoules, so there is a potential efficiency gain of around 25,000 times.
25,000 times? That's not just an improvement, that's a different league entirely. But the title of the research paper itself hints at a mirage. What's the catch? Is this a lab curiosity, or does it genuinely threaten to upend the way AI is built?
That's precisely the core question. The research introduces a fascinating approach, moving beyond electrons to what they call light matter particles. But as with many early-stage breakthroughs, the spectacular numbers often come with significant caveats regarding scale, environment, and the specific tasks being performed.
Okay, so it is important to unpack that 4 femtojoule claim first. As was mentioned, it's a massive leap. What exactly are they measuring, and under what conditions? Because often these ultra-light, ultra-fast demonstrations are operating in highly controlled, perhaps even cryogenic environments.
That's a crucial point. The 4 femtojoules figure comes from experiments with what are known as polaritons. These are hybrid particles, a blend of light and matter, specifically excitons within a semiconductor structure. The researchers are performing what's essentially an analog computation. They're not doing standard digital logic. They're using the physical properties of these polaritons to mimic neural network operations, like matrix multiplication, directly.
So it's not a general-purpose CPU crunching numbers. It's more like a specialized calculator designed specifically for one type of math that AI heavily relies on.
Exactly. One might think of it less as a new microprocessor for a laptop and more as a highly specialized accelerator card. The efficiency comes from several factors. First, polaritons dissipate far less energy as heat than electrons do. Second, because they're part light, they move at optical speeds, which offers potential for faster operations. And third, the analog nature of the computation avoids the energy overheads associated with converting signals between analog and digital domains, which happens constantly in traditional digital AI chips.
That makes sense. It's like comparing the fuel efficiency of a Formula One car on a pristine track versus a family sedan in stop-and-go traffic. The Formula One car might get incredible mileage under ideal conditions, but it's not going to replace a daily commuter.
That's a very apt analogy. The researchers demonstrated this efficiency in a very specific small-scale setup. The device they built is essentially a single neuron, or a very small network, performing a single type of operation. Scaling this up to the complexity of a modern large language model, which can have billions or even trillions of parameters, is where the mirage starts to become apparent.
And what about the operating environment? Is this technology capable of running in a data center at room temperature, or does it need a super cold lab?
The paper indicates these experiments were conducted at room temperature, which is a significant positive. Many exotic computing approaches require extreme cooling, making them impractical outside of specialized labs. So that's one hurdle they appear to have cleared, at least for this initial demonstration. However, the stability and long-term performance of these polaritonic systems at room temperature, especially when scaled, will be a critical area of future research.
Okay, so the efficiency is real for what it does. And it's room temperature. That's impressive. Can you explain more about the light matter part? What exactly are these polaritons, and how do they actually compute? Electrons are electrons, and their flow is well understood. What's happening here?
At a fundamental level, polaritons are quasi-particles, formed when photons, particles of light, strongly couple with an excitation in a material, often an exciton in a semiconductor. An exciton is essentially an electron and the hole it leaves behind, bound together. So there is this hybrid entity that behaves both like light and like matter.
Like a half-light, half-electron particle? That sounds incredibly fragile.
They are, but precisely because they have both light and matter characteristics, they can be controlled using both optical and electrical fields. In this Penn research, the polaritons are created within a specially engineered material, a microcavity with quantum wells. They are then guided and made to interact. When these polaritons interact, their behavior can be designed to mimic the mathematical operations of a neural network. For instance, the intensity of one polariton beam can affect another, allowing for weighted summation, which is a cornerstone of neural network computations.
So instead of electrons flowing through transistors representing zeros and ones, there are these light matter waves interfering or combining, and the resulting intensity or phase represents a value in an analog computation.
That's a good way to visualize it. The output isn't a crisp digital 1 or 0, it's a continuum of values. The beauty of analog computing for AI is that these interactions can happen simultaneously and locally, reducing the need for massive data movement that plagues traditional digital chips. That data movement is a major energy hog in current AI hardware.
So it's inherently parallel and potentially very energy efficient for specific types of operations. But analog computing has historically struggled with precision and noise. Does that apply here?
Absolutely. That's another part of the Mirage. Analog systems, by their nature, are susceptible to noise and variations in manufacturing. A slight imperfection in the material or a tiny fluctuation in temperature can lead to errors that are difficult to correct. Digital systems, by contrast, are far more robust because they just need to distinguish between two states. For many AI tasks, especially at inference time, some level of imprecision is acceptable, even beneficial, as brains themselves are analog and noisy. But for training, or for tasks requiring high precision, it becomes a significant challenge.
So this isn't going to replace the GPUs used to train the next generation of large language models, at least not in its current form. It's more about running those models once they're trained, and even then, perhaps only specific parts of them.
That's the realistic assessment. The researchers envision this primarily as an accelerator for AI inference, where a trained model is used to make predictions. For tasks like image recognition, natural language processing, or sensor fusion at the edge, where power efficiency is paramount, this could eventually be transformative. But for the massive, iterative, and high-precision computations involved in training, digital systems still hold a commanding lead.
Regarding scale then, as was mentioned, this is a small demonstration. How would one even begin to scale something like this up to the millions or billions of interconnected neurons seen in modern AI models?
That's arguably the biggest engineering hurdle. The current device is a proof of concept built in a highly controlled lab environment. Scaling requires fabricating billions of these interacting polariton structures on a single chip, ensuring uniformity, managing heat dissipation, and interfacing reliably with conventional electronics. The manufacturing techniques for these novel materials and structures are vastly different from established silicon fabrication processes.
Other attempts have been made at optical computing or neuromorphic chips that haven't quite broken through the silicon barrier. What makes this polariton approach different? Or is it just another contender in a crowded field of exotic computing architectures?
It's definitely another contender, but it does have some unique characteristics. Many optical computing efforts rely on traditional photonics, where light travels through waveguides and interacts with modulators. This polariton approach introduces a hybrid light-matter state that allows for stronger, more efficient interactions at smaller scales than pure photonics often achieve. The Penn team's work is part of a broader push to find alternative substrates and mechanisms for AI computation that aren't bound by the electron-based limitations of silicon. Other approaches include memoristors, superconducting circuits, and various forms of quantum computing, all trying to solve the energy and speed bottleneck of current AI.
So while the 4 femtojoules is a staggering number, it's important to remember it's a benchmark under extremely specific, idealized conditions for a nascent technology. It's a proof of principle, not a product spec.
Precisely. It signals a promising direction in fundamental physics and material science for computing. It shows that there are pathways to dramatically lower energy consumption using non-traditional particles. But the gap between this kind of lab demonstration and a commercially viable, scalable product is vast. It requires overcoming challenges in material science, fabrication, system integration, and software development.
It sounds like the technology is still a long way from replacing NVIDIA's data centers with light matter chips, but it points to a potential future where AI accelerators might look very, very different.
Indeed, this research is a powerful reminder that the exploration of new physics for computing is far from over. The limitations of silicon are driving innovation across multiple disciplines. Whether polaritons specifically will be the answer, or if they'll inspire the next generation of breakthroughs, remains to be seen. But the idea of harnessing hybrid light matter states for computation is certainly compelling.
So, to summarize the key insights from this Penn research on light matter AI chips, first, polaritons offer a novel and potentially ultra-low pathway for AI computations, achieving efficiencies orders of magnitude beyond current silicon. Second, the stated 4 femtojoules per operation, while technically accurate for the demonstration, is highly context-dependent. It represents a single specialized operation in a lab setting and doesn't directly translate to the energy consumption of a full-scale general-purpose AI chip. Third, this technology is positioned as a specialized analog accelerator for AI inference, not a replacement for the digital processors used in AI training or general computing. Its strengths lie in specific, highly parallelizable tasks where some imprecision is tolerable.
And finally, significant engineering and manufacturing hurdles remain before such light matter chips could ever move from a scientific breakthrough to a practical, scalable technology capable of widespread adoption.
This research really highlights the ongoing tension between what's possible in a lab and what's practical in the real world. It raises the question of whether more of these specialized, highly efficient, but narrowly focused chips will emerge as AI demands grow.
And what types of AI applications, perhaps those at the very edge of edge networks where power is at an absolute premium, would justify the immense investment required to bring such a fundamentally new computing paradigm to fruition?
That's all for this episode of Tech Disruptions. Join us next time as we keep exploring the technologies reshaping our world. Thanks for listening. We'll see you next time.
Stay curious out there.